All right, the last type of intermolecular force we want to talk about is the London dispersion force, or the induced dipole thing. This intermolecular force is present in everything. All molecules, all atoms exhibit London dispersion forces, or induced dipole forces, okay? Most of the time, unless we're dealing with really big molecules like polymers, most of the time, the other intermolecular forces are more important. And so we kind of neglect this one unless we're dealing with nonpolar things. If we're dealing with only nonpolar things, then this is a really important intermolecular force. Remember that the attractions and repulsions that we see between molecules or between atoms is always a combination of all the possible intermolecular forces that can be there. Okay? We've talked about them like only this one exists and no other one exists. But in reality, a bunch of them exist for a given molecule. What we've been talking about is the one that's the most important at that point in time. Okay? So in this case, this exists everywhere all the time. We are going to talk about it with respect to nonpolar things because that's where it matters the most. Okay? But this lets us figure out why we can have molecular solids. And I like this example. Like you probably heard me use this example in Gen Chem 1 to explain some things too. But if we look at chlorine and fluorine, they are gases. And if we go down that column, if we got a table, bromine is actually a liquid, and then iodine's a solid. Right? Those are nonpolar things, so they don't exhibit dipole forces or any of that stuff. So what's the force that holds them together? Well, it has to be this induced dipole force. So what do we mean by that? What is an induced dipole? Well, we saw that a minute ago with the whole water and oxygen thing. But how do we induce a dipole if we don't already have a dipole? Right? Because we had water, and that makes sense. It's polar. It can shove an electron cloud around. So how do we introduce a dipole if we don't already have one? That's what we got to figure out. And again, these things are present in everything. We'll talk about them with respect to nonpolar things, okay? Okay, so yeah, how does it work? Left-hand side, two molecules. Electron clouds, time average, basically a sphere, okay? But take a snapshot at any given time of these molecules, and those electrons, remember, from the classical point of view, you can kind of think about them as being in orbits around the nucleus, right? From the quantum mechanics point of view, we know that's not really true. We have those orbitals, the 1s orbital, the 2s, 2p, all those things, right? And the electrons are somewhere in those shapes, right? Remember, the s orbitals are spherical, the p orbitals are like dumbbell shaped, the d orbitals are four-leaf clover shaped, and the electrons are somewhere in those. Where are they in those? We don't really know, somewhere, okay? But if we were to take a snapshot, we'd see electrons in particular places in those molecules, right? So it's possible to take a snapshot where we have an imbalance in the electron cloud. And so we have a dipole, instantaneous dipole, we call it. But on average, those things average out, right? So what happens is if you bring two molecules close enough together, they can kind of correlate their electron movements. So in this case, we have a snapshot where the electrons are in both molecules offset this way, right? On the left-hand side of the molecule, there's more electron density than the right-hand side of the molecule, right? So now what happens is they see this attractive force between the positive and negative, just like you would in a regular dipole-dipole interaction, right? And now, because of that attractive force, they're in a lower energy state than they were before. And now their electron movements are correlated, which means they move together, right? So if you want to think about it like an orbit, now the electrons are doing this. They're synchronized, okay? And because of that, now we have this permanent attraction through what was an instantaneous dipole. Does that make sense? Are you guys okay with that?
So could Could one instantaneous dipole cause other things to become instantaneous dipoles?
That's exactly what happens, yeah.
So even if just one goes, like the neighbors will start to be attracted to it, and then that's.
And that's how it happens, exactly. Right, and that's why they're present in everything all the time, because that's always happening.
Okay.
This is the weakest type, right? This is the weakest type of intermolecular force because we're dealing with partial shifts in electron clouds only, okay? But when you have really big molecules, those shifts can be really big, and so those can be pretty strong attractions. Okay? So this depends on that concept of polarizability that we talked about before, the ability to distort that cloud, right? The more we can wiggle that cloud around, the more attracted they can be to each other. So the bigger the molecule, the more electrons, the more spread out the electrons, the more wiggling of those electrons, and also the more surface area available for interaction, okay? So these forces increase with molecular weight. So again, higher molecular weight, the larger your induced dipoles can be because the electron clouds are bigger. So the stronger your interaction between, because now we've got a bigger dipole. So that means that it takes more energy to break those forces apart. And that yields a higher boiling point. So if we have something like, do you guys know what I mean when I say the word hydrocarbon? No? That's okay. So hydrocarbons are things that are made of carbon and hydrogen, like this. This is methane gas, okay? Or we could have, let's not do it that way. There we go.
Hydrocarbons just carbon?
Just carbon and hydrogen. That's why they're given that name. These are different hydrocarbons. They're nonpolar things. They're made of only carbons and hydrogens. And you can see that their molecular weights are increasing, right, as I go and add more carbons and hydrogens to it, right? So take a look. We've got different hydrocarbons here, right? The first four, so that's methane, ethane, propane, and butane. And you can see that their boiling point on the y-axis and their molar mass on the x-axis makes a nice straight line, right? So we are directly and linearly proportional to the molar mass. That's because of that polarizability that we talked about, okay, that electron cloud size. So this leads to some pretty interesting stuff. In iodine, you've got the induced dipole interaction causing those iodine molecules. So we have an I2 here, and we have an I2 over here, and they're attracted to each other, right? And so we get enough of those I2s, and they become a solid. And so we get crystals of iodine, little purpley black shards, right? But as soon as we apply a little bit of energy and we overcome those intermolecular forces, which are not hard to overcome because it's just induced dipole forces, there's nothing else there, right? They're not chemically bonded other than I2s here separate and I2s here, right? So they can go directly into the gas phase, and that's called sublimation, right? We go from solid to gas. And so the cool experiment to do is you take some iodine solid and you heat it up on a hot plate, you put it in a beaker, you put a watch glass on top of it, you put a little ice in that watch glass on the top. So you heat it up, you get this nice purple smoke inside because you're creating iodine vapor. And then as the iodine vapor hits the cold glass on the top, it goes right back to a solid again. That's called deposition. And so you can grow little crystals or little stalactites of iodine off the roof of that thing, right? So you got iodine at the bottom, you got a purple gas in the middle, and then you got iodine things growing off the top of it. Okay, so if you only remember one slide out of the last 2 days, this is the slide to remember, okay? It shows you all of the intermolecular forces. It shows them to you in order of strength. Ion dipole being the strongest, induced dipole being the weakest on average, okay? It tells you what causes their strength of interactions. You know, for example, the charge of the ion, the magnitude of the dipole, the distance in between, right? Polarizability. And it gives you an example. This is wraps everything up from 2.5 hours of lecture in a slide. Okay? So learn the slide. It's really important. I like to show this picture because this picture shows how all the different intermolecular forces play a role in contributing to the overall attraction between molecules. So if we look at argon over here, argon has only London dispersion forces, or induced dipole forces, right? But if we look at something like HCl, HCl sees a dipole-dipole interaction because that's a polar molecule. It also sees dipole-induced dipole. So even though we have a polar thing, we can induce a greater polarizability when it interacts with the electron cloud of its neighbor, okay? We see induced dipole, so again, the same kind of thing. And all of that added together contributes to this total attraction that you see in blue right here, right? And we don't dwell on the details of that because the details of that's outside the scope of this class, okay? Just know that the overall attraction is because of all different types of intermolecular forces, all right? What I want you to be able to do is when I give you a molecule like NH3, I want you to be able to tell me that that's nitrogen bonded to hydrogen. And so the strongest type of intermolecular force that you should see in this thing is what? Hydrogen bonding, right? Or when you see HBr, this is a linear molecule. Those things are not the same. So this is a polar molecule. So this thing would exhibit dipole-dipole forces, right? And so something like HBr would have a higher boiling point or a lower vapor pressure as compared to something that's roughly the same size but nonpolar, right? That's the kind of stuff we want you to take away from this chapter. Okay, if you're trying to figure out what type of intermolecular force is present in a molecule, I take the common sense approach to it. If you're a kind of person that likes a flow chart, here's a flow chart that you can go all the way through from the beginning and say what type of intermolecular force, or really the question you're answering here is what's the strongest type of intermolecular force that's present, okay? Do I have ions, yes or no? Do I have polar molecules, yes or no? Do I have nitrogen, oxygen, or fluorine bonded to hydrogen, yes or no, right? All the questions that we would ask ourselves from a common sense point of view, but this gives you a nice pathway to do that if you're the kind of person that likes that thing, okay?